Move on to the next paper, which is by Chuck Mims, who was, I should say, with Exxon Research and Engineering, now at the University of Toronto. His title is Residence Time and Coverages of Surface Intermediates During Fischer-Tropsch Synthesis.
Eyes are getting more and more useful as more and more gadgets are attached to the speaker in scientific meetings. Thank you, Alex, for the introduction. To introduce the talk, I want to acknowledge the people that worked on these studies with me. Another who left Exxon actually a couple of years ago, Jim Produski, was my technician. He's gone to Bell Labs and is busily doing superconductor work. Ken Rose and Mike Melchior are both NMR experts, and were very valuable in analyzing some of the more detailed results of the isotopic transients that I'm going to talk about. Well, having to go to an academic setting and start to teach, I started looking at notes on catalysis and ran across this quote by Hugh Taylor, which I thought was amusing because I hadn't seen it in a long time. And it says, when the stages of an overall catalytic process can be described in terms of well-defined succession of chemical processes, the details of which are well understood or quite plausible, and there's a big range there, then the necessity for such a word as catalysis to mask our ignorance is no longer necessary. Now, catalysis has taken on enough subtlety that I don't think the word's in any danger, even if we do understand it all. But what's clear from this symposium is that because of a lot of excellent work, we are past the plausible stage. There are probably too many plausible mechanisms at the moment. And all of us are trying to find the well-understood part of the mechanism. And generally, the things that are well understood are those that are performed in a computer or on simple model surfaces so far. Trying to unravel what's going on in steady state is still, I think, one of the most important things that we can do. But with that in mind, I wanted to list what I will talk about, and it's, especially if I run a little long, it will be totally isotope transients, in which the questions that we asked in the work were in order of our curiosity: how do the chains grow and how fast do they grow? We actually spent more time looking at the higher hydrocarbons than C1 products. By the time we published a lot of very excellent work that had been done on the methane formation by Alex Bell. You've heard a lot of it today, and also there's already been some work on higher hydrocarbons produced by Paul Bloom and software. But anyway, we got into the game. So I want to talk about the steady state mechanism as revealed by isotopic transients investigating the higher hydrocarbons. If I have time, I'll jump into this reversibility of chain growth that's cropped up a little bit here, and then probably won't have time to say much about the identity of intermediates, except as the evidence of the experiment revealed itself. Over the years, this is the plausible mechanism in its very simplest form, where we grow higher homologs of the precursors on the surface to give us our products. This is a very streamlined mechanism. This box hides an awful lot, as we've just heard from a lot of the people in this symposium, and I have a small list of these in the next view graph. And one of the questions that has come up now, both in Dr. Shusterovich's talk and also yesterday in Al Beckman's talk, is how does the CO dissociate? Does it get hydrogenated first and then dissociate, or do you get a prompt manufacture of bare carbon atom? And of course, from the other talks we've heard today, representing carbon on the surface by one species is also a dangerous thing to do. But this tracking of the CO activation is one thing that we learned a bit about in some of our experiments, and I'll show you that right now. First catalyst we looked at was cobalt, and it was cobalt and silica in a very high weight percent, very low dispersion, and the hope was to get away from any sort of support effects that might be involved did was ran it in 2 to 1 hydrogen CO at 200 degrees C, roughly, at small conversion. But it performed as a good chain growth catalyst. Our alpha was about 0.8. We had fairly high molten to paraffin ratios. And blessedly, we made a few percent of methanol from this reaction. And when we performed these isotope switch at steady state, from C12 to C13, we followed the carbon 12 and 13 content of all the products that we could follow. With time, the solid dots here that colored red are all the hydrocarbons that we measured except for methane on this catalyst. They track one another very well in terms of their carbon 13 content, showing that a single residence time distribution was dominating the precursors to all these hydrocarbon chains. The methane has an additional tail, and we've heard about what might produce this tail. So there's a vat full of carbon that actually spends a longer amount of time on the surface. Alternatively, there's another source of methane. But the higher hydrocarbons all follow the same residence time. Now we could get GCMS information, and that's what's shown in the upper curve that actually generated this total amount of C13 in the butene product you see here. We also tracked to do even more detailed work on the internal isotope distribution. Unfortunately, again, because of the low sensitivity of NMR and the low conversion here, we had to smear our time resolution to get, but we still get a good average residence time for each carbon atom now in all of the products visible. And for this catalyst, we saw identical parallel growth of carbon 13 to every position. These are the alkenes that we managed to look at with the same. The methane is has slightly less C13, and that's because of that tail starting to show up already this date. And then the little trace of methanol had roughly the same. It was slightly faster actually at the longer. We tracked 2 windows during this transient, at the window at a higher time, the methanol had actually been a little bit more completely exchanged. So if anything, it has a slightly, speaking in averages here, a slightly shorter residence time distribution on the surface than the precursors to all the growing chains. Spending a little more time on the growing chains, there are a couple of mechanisms that could give you this. One is scrambling, the other is a rapid selection of 4 carbon atoms out of the precursor pool. They both should give you a statistical distribution of the isotopicals, and that is what we see. And if you go integrate all the carbon that shows up in all these products through the transient, you find that you can say that the chain growth have to be then very fast on the time scale of the exchange of the precursor vat, and that places limits on that time scale, given the fact that it's a nominal measure of the time constant for the precursor vat, about 20 seconds. So it takes less than a half a second to grow one of these. Because of that, surface coverage has to be low. Provided this chain growth is irreversible, it has to be low, and so that there's a very small number of growing chains on the surface at steady state. We looked at this transient as a function of temperature and gas composition and found a weak dependence of the coverage with temperature and gas composition, and therefore those parameters were affecting the rate constants more than that coverage is on the surface. But returning to the methanol, it has roughly the same time constant, and therefore its precursors, the simplest assumption, are also associated with this vat of C1 precursors. The methanol, as was found by Katzer on rhodium, in our case, this adjunct, this minor product, is a non-dissociative pathway. When we have do a double label experiment, we see no scrambled methanol. So if you then take both of the things precursor and it isn't dissociated, then that means that most of the carbon sits here parked, undissociated, during its residence time on the surface. It does not say that an oxygenated species is the monomer for chain growth, because you could have a short-lived species intermediate between these, but it just says that most of these C1 precursors have this bond. It's also, as we've seen with other catalysts, not chemisorted CO. It's the majority state, but it's very easily exchanged. This is an irreversibly bound species, so the presumption is that it's been hydrogenated. There's a chance it could be one of these odd lying down COs that's irreversibly absorbed. We don't know. Because I haven't done any hydrogen tracing. I understand that we're going to hear some more later in the session about the hydrogen associated with such a precursor. So that was those were our results on cobalt. So we learned a little bit about the C1 bath by watching this thing in steady state in a relatively messy system. When we went to ruthenium, we saw a different behavior. Instead of all the hydrocarbons showing a similar decay, this again is this line represents the time at which we switched from carbon 12 to carbon 13 CO. Again, the methane showed this a long time tail again, but we saw different time constants for this C2 plus hydrocarbons. And the reason for that was that the carbon atoms had two distinct residence time distributions on the surface. One of them was associated with the last two carbon atoms on the alkyl, these growing chains, which took longer, although be replaced from the surface. And as you grew longer and longer chains, these things were pushed away from the double bond. And the ones added subsequently are all have another characteristic time, although there may be a trend in there, but I don't know. There was no methanol co-product in the system, so we couldn't test the likelihood of, the existence of an oxygenated precursor from these experiments alone. And the question is why? There's something happening at the C2 stage. And is it a C2 or is it one of the C1 initiators that combines your first C2 intermediate? We addressed that question, but before I get into those results, let me show you again just the results of integrating the amount of carbon that came off the surface during this transient. And again, we find a small amount of carbon when normalized to the number of surface ruthenium atoms, like 3%, one carbon atom, active carbon atom in this precursor bath for every 30 surface carbon atoms. Most of the time that the monomers out here spent on the surface are spent as C1s and not as growing chains. Again, the lifetime of the growing chain is very short compared to that, and therefore the coverage of these actively growing chains is very small. Now the C2 stage, there are a variety of mechanistic constructs that could give you a longer residence time at this stage. The question was, is it a real C2 intermediate containing two carbon atoms, or is it the result of an additional, say, a longer residence time carbon atom adding to C1 prime to nucleate the growing chain, and the identity of those two is lost in subsequent chain growth. By looking at the internal label distribution of the C2 groups contained in these hydrocarbons, here we're able to determine that yes, it spent at least half of its time on the surface as a C2 species with a distinct residence time. So the question I ask, I'm going to jump ahead here and speculate and come back to it later. One of the systems that we've gotten good data and understand quite well from the surface lamps people is a Philodine. I wonder whether as a storage unit of C2s that Villadine might be the C2 unit. And again, referring to the work that or similar work to what Alex Bell referred to from Mike White's group, the Villadine does decompose at quite low temperatures on ruthenium, the basal planes. Without co-adsorbed CO, if you put CO next to it, it lives a lot longer with much higher temperatures. And in fact, this decomposition rate is determined by the desorption of CO from this co-adsorbed layer. And so in Fischer-Tropsch conditions, perhaps this thing is held in a nice little cage where it can't lose hydrogen to the surface. And that's a speculation at this point, but I think that this is coming at the mechanism from these two different angles is going to pay off more. The chain growth rates, again, it's not news to anyone, is now quite fast. This slide just compares the numbers we got these are all 1 atmosphere data. These are lower limits to the time it takes to grow, to add carbonate, growing chains on these 3 catalysts, so I didn't talk about iron. It's very similar to cobalt, except it didn't produce oxygen. And we weren't aware enough of the possibilities of looking at the time. But this is compared to the earlier transient work using step concentration techniques from the people at Shell and some work by Paul and his group in recent years. So the really nice thing about the isotopic transient technique is that you know you're looking at the players in the game and not as spectators. Or if you look at backwater pools of current, it will show up as they will show up in proportion to their participation in the mechanism. I just wanted to say one thing about the growth and maybe the depolymerization of the beta carbon, as it's been called, about showing results of an experiment where we also ran for a while. This is quite a long time in the C12CO and then switched to C13CO. The red dots are now the C13 content in the methane and in the C4 hydrocarbons as a function of time after the switch. It's a break here while we sat in C13 for roughly 10 minutes. And then we switched into hydrogen. And not only do you get the big peak in methane, you also get some higher hydrocarbons, which has also been shown by other workers in the room. But during this, we looked at this C4 fragment coming off at its internal isotope distribution. And if this were a result of some very slow chain growth on inactive patches, then you would expect to see C4 fragments that contain 1, 2, 3, and 4 C13 carbon atoms, whereas if they grew rapidly, then you get the result that we actually saw, which is you have a lot of them have all 4 of them C13, and the rest of them that grew during the initial period are all C12, and there aren't any in here. And this is basically the amount we fail to match the isotopic abundance of C13. Okay, how am I doing for time? Fine?
Yeah, another 2 minutes.
Okay. Well, I just wanted to say one other thing to investigate the depolymerization and reabsorption during chain growth, and this addresses one of the same aspects that Bert Davis talked about. We were concerned that the actual scrambling of that rapid polymerization and depolymerization of the growing chains would also produce the scrambled isotope distribution, or an even isotope distribution in the longer chains. And while that would have nothing to say about the speed of chain growth, it would still have to be very rapid for that to occur. It would have a different message about the number of them on the surface if they're sitting there. And we didn't expect to see much, although Tamara had done some very nice work at lower pressure showing that there is some depolymerization. We added hexene to the CO hydrogen in this mixture, and when we increased it 200-fold, it was a native production rate. We were able then to see an effect in the lower hydrocarbons. We also saw some of them absorb and grow longer, but we saw saw it here with methane without changing its overall appearance rate, so it's contaminating the monomer bath. And then in C4, we actually went in and looked at the isotope distribution. Obviously, the increase in C3 and C5 also contains some C12. In this case, we used C13 carbon monoxide and C12 hexene, but we didn't examine those in any detail. The question is how much of this is depolymerization and how much of it is complete scrambling and reassembly. So if you look at the internal distribution of the butenes, you see a result that's intermediate. If all you had was an additional polymerization from CO and depolymerization from hexene, you get distribution in C13 content that looked like this. If it was rapid assembly and reassembly, you would get a statistical distribution like this at 50% C12. We never hit 50% by but bracketing, you can see that the distribution is intermediate and in fact favors this a little bit. The conclusions, though, from this work is that under the steady state conditions, at least reabsorption and depolymerization was not a significant scrambler. The carbon content really changed, and that they were reversible. And that concludes what I wanted to say, and I will list them if you want. If you didn't pay attention, I wouldn't have to slides. I won't do it.
Could you say again, what was the role of this ethylidide in intermediate in the Fischer-Tropsch?
I don't know.
But
I speculate that.
have you identified the presence?
No.
Oh.
Let me show you. There are two things.
You mentioned you have C2 intermediate.
Yep.
So what is your C2 intermediate and intermediate important for what?
If I can't find it is a C2 intermediate that is either in the main chain growth path and is relatively unreactive. And that shows up as a longer residence time for it to react. Or it could be a storage pool of a species that is not on the main path, but it gets trapped in there and is reintroduced into the system on a time scale that one can see. This technique cannot tell the difference between those two. You solve the equation, you can't tell.
So you cannot say it's really important for CC chain growth or just maybe a spectator or whatever?
That's correct. It is it's not totally a spectator. It may just spend some time idling before it gets in the chain because it appears, these appear in the products. We're not examining them on the surface. I can't find the slide, but we want to look for it. And finding such a species in the middle of all of the beta carbon on the surface spectroscopically would be very difficult because the quantity is less than 1% of the one. In fact, it's much less than that. It's sort of 1 for every 300, I believe, ruthenium atoms on the surface. So that's a small quantity to see in the presence of multi-layers eventually of carbon. The oxygenated intermediate on cobalt, that coverage turned out to be 1 for every 3 surface cobalt atoms. And we made a quick pass, Fritz Hoffman and I made a quick pass to try to see that on a model cobalt catalyst in infrared. It failed, but we hope to get back to it if someone else hasn't found it before we do it.
Yeah, Cal?
Chuck, in drawing your reaction sequence, you showed formation of an alkane going in an equilibrium with an alkene.
I did.
I thought you did. The basic diagram that you showed.
Okay.
I want to understand that.
I can see it, but you can't. AICHE should give me a course in graph management. We're very thankful.
You have it up.
Yeah. Would you like to come on that?
Maybe you can describe it in words.
Yes. I think what
you showed was the formation of a C1 and then, or I mean a C2, and then that you had arrows going in equilibrium with the C2 double bond.
Let's try this one. That one doesn't have it. Okay?
Yeah. Well,
The other one.
What you would show is the bottom C2 there had a double bond on it. And what I'm asking is, are you implying that the primary intermediate is an alkane or an alkene?
No.
Yeah, there it is.
There it is.
Yeah.
And all I am implying by that is that there is a surface precursor. All this the box means is it's a surface. This means it's in the gas phase, and we paid a lot more attention to alkenes than alkanes since they were our predominant.
So you're talking
product.
about a C2 surface species that is
Yes.
a precursor to an alkene, which is...
Something we might not understand is that maybe precursor to C2 contains 3 carbon atoms.
Yeah. So
It's
you're...
possible, but this was a surface precursor to the gas phase C2 products. That's all that.
So the alkenes are your primary products.
His reversibility addressed the question of reabsorption.
Okay.
Thank you.